Hello, everyone. So I'm Pratyay Banerjee, a master's in computer science student at UIC, and I have done a project on large language models using the concepts of cloud computing as part of CS441 by Professor Mark Grechanik. And here, let me share my screen and get started. Hopefully, you guys are able to see the screen. So let me get started. So here we have built a large language model using the concepts of cloud computing. And we have programmed the project using the Scala, the functional programming language. And we have used concepts of distributed cloud computing. We have used Apache Hadoop's MapReduce functionality for like processing a large data set and like generating vector embeddings from them and finding similarities between the word. And we have used finally we have deployed the project on AWS EMR. So let me just go through the steps that we have like followed in the project. So first we have cleaned the data and divided it into shards, and then there are several MapReduce jobs which does they're like one by one which like the first one converts the words to token and generates the frequency of each word in the text. The second one is the tokenizer job, which one is like the first, it's kind of similar to the first job, but the thing is the first job, word to token job, it generates the input in a sorted order. And we don't want the tokens in a sorted order. We want it in the in the order of the input, because we will feed these tokens later to the embeddings, like the token embedding mappers, and which will use these tokens to understand the context of the words and understand the semantics and generate the cosine similarity of the words. So the first word to token job is just a standalone job, like it's for the requirement of this project. We needed to create a job which will convert the word to tokens and as well as generate the frequencies of each word in the text. So that's why the first job was created, and it is not getting used in any of the the output of this job is not getting used in any of the other map reducers. The second job was that's why it was created, because it creates the output in the order of the input. So let's get started, and I'll show you guys the code once. Uh, so this is the code. So here on the left hand side, if you guys see there, the MapReduce functions, MapReduce classes. So the first one is the word to token job, which creates the words from tokens and has like the outputs of frequency of the words as well. And then I have the tokenizer job, which uses the tokenizer mapper and reducer, like which tokenizes the words in a sorted, like in the order of the input and not in the sorted order. And then we have the token embedding job, which will generate the embeddings from the tokens of the previous job. And then the cosine similarity driver job, which will generate the cosine similarities of the word. So let's get started and let's see this how this looks in AWS EMR. So I've already created a cloud like S3 bucket, the cloud CS441, which has the input shards for the first job. And let's see here, these are the shards. So I've taken a little bit small data set for demonstration purposes. So if you guys want to take a look at how the data set looks like, the input shard. So this is one of the input shards. So this is a chunk of text, and we will use this as the input for the first MapReducer. So let's get to the AWS cluster, and this is uh, the first cluster, my cluster on AWS EMR. And here we'll have to create the steps to run the first job. So I would say word to count job, word to token job, sorry. And here we'll have to browse and provide the location where the jar is located on the S3 bucket. So here, this is the jar, and I will provide this command to the command line for this AWS EMR. So this tells AWS EMR to click which job to run, and then the input, which is the input shards, and the output. So for the output, we'll be using HDFS. We'll see how the output looks in HDFS. So what we are expecting from this is this will generate the count of each word as well as the tokens. So let's see. I've started the job and it will take some time. So we'll connect back once this job ends. So I'll reshare my screen again since the job has completed. And so here, hopefully you guys can see the screen again. So here, as you guys can see that the job has completed, right? And this is the word to token job that we started. And we can see the output of this job in HDFS. So here, what I did was just basically here, if you select on the applications, and then if you go to Hue, you'll be able to redirect it to this. Here you have to select files, and you'll be redirected to this, and where I have mentioned that the output folder, like for this job, like we mentioned it in the steps, this is the out folder for the word count, and this is the part.r00 files which the reducers create. So let's take a look at the output. So here, as you guys can see, that there were some numbers which are present first, and there are the words. So here it is in a sorted order. That's what I was talking about. That's why we had to create another MapReducer where the order was not sorted and it was like the same as the input order. So here, if you can see, that is the word. Then these are the JTOKEN tokens, and this is the frequency. That means that the word abandoned was present in the input text 26 times, right? And same for the other words as well. So this is how the output looks like. And all right, then let's move to the next job. So now we will talk about the next job, which is the tokenizer job. And for that, we will have to like start a new job and add the steps again. So for as we were talking, so for the next job, we will run the tokenizer job, which will generate the order, like generate the tokens in the order of the input, like as it was in the input of the text. So for that also we have sharded the text, and we have pre-processed it a little bit so that the mapper and reducer automatically shuffles and sort. So that's why the order was messed up in the previous one. Like the order was in a sorted order. But here we need to preserve the order. Like so that's why what we have done is while sharding the text file, we concatenated each word with its position. So if you take a look, I'll show it in my local. So here, if you see, like every word is concatenated with its position. So that's why we will be able to maintain the order of the output. So let's create another job. We'll have to add this step. Is a job. We will provide the job location. And with the command. So from here on, we will only be using HDFS and not S3. So, but this like folder doesn't have the shards. So we'll have to shift the shards from S3. So right now the shards are in S3, as you can see. So we'll have to put the shard in it. like HDFS. So I've created a directory called input text shard. Now I'll have to like run this command, which will move the shards from S3 to HDFS. So as you can see, the shards are there. Now, if you want to go and check in Hue, you should be able to see in the input text shards, the file should be present. And we have given this as the input to the step. So what are these arguments? So I'll just briefly talk about this. So this is the input path, and this is the output path where the mapper and reducer will run, and like it will generate the word and the token IDs. And this one is the number of reducers I've set here. And here, so what the rest of the arguments are is that the mapper and reducer will generate like it generates the output in a key value pair. So here we are like printing the output, like what we are generating is a word and its tokens. But for the next mapper reducers, we just want the tokens. We want to extract the tokens from this output. So here we are passing another path. So this token IDs.txt. So this will get created. So this file will get created, which will contain only the token IDs from the like from the output of the tokenizer job. It will consolidate the token IDs, like it will consolidate the token IDs from all the part.r00 files that the reducers created from this previous job, tokenizer job. And then it will shard it. And here, this is the location of the shards. And this is where I have given the like it means the 50,000 lines per shard. So this output, the shards will contain only the token IDs. So let me go ahead and run it. Let me just check if I'm missing anything. So the output is there. Let me just go ahead and start it. All right, let's see. So now the job has completed, and as you guys can see, so this was the job that we ran, the tokenizer job, and we provided these arguments, and this is done, this is completed. So now we want to see the output, right? So from this, what we are expecting is first this job to generate like the words and the tokens in an order, like the order in the order the input was, like to maintain the order of the input. That's why this job was created. And then as a post-processing step, what we are doing is like we are extracting the token IDs from the output, and then uh, we are consolidating those token IDs and creating a shard file from this. So this was the log. As you can see, the mapper and reducer ran, and this got completed. So now we are going to see the output. So this is the folder that we were in, and this is the output. That is the directory that we created. This was one of the first job, and this is for this job, tokenizer job. And as you can see, these are the part as user files for the different number of reducers. So as you can see that this is the output. So the first is this is the position that was concatenated with each word, the position, the word, and the tokens. Now, what an interesting thing is here, as you can see, we have maintained the order, which wasn't the case for the previous one. If you see the Robert Boulder is an English film, then full stop, television and theater actor. He had a guest starring role on the television series The Bill in 2000. You can see, if you want, you can verify this from the shards that we first created. If you can see here, uh, you can see that this is the exact way the input text is. So that is, we have been successfully able to maintain the order of the input. And then as a post-processing step, what we did was we extracted the tokens from each of the reducers. As you can see, there were a lot of reducers created because it was a large data set. And then we like consolidated, we extracted the token IDs and we consolidated the token IDs into a single file, token IDs of txt, and then we sharded it. And this shard folder will be the input to the next mapper reducer because this contains the sharded tokens. Here, if you can see, this is just the token IDs and it is in the same order the input was. If you see, let's verify. So 0, then Robert Bolter. So this 28, then 35362, 33, 11206, 466. If you see, the token IDs are in the same order. That means that we have been able to preserve the order of the input. So what we did was we uh, like concatenated the position with each word and then passed it to the mapper reducers, which then generated the order, like the output in a like we maintained the order of the input. And then what we did was we extracted the token IDs from that reducer output files, and we consolidated it in a token IDs.txt file and then sharded it. So this will be the output of the next mapper reducer, because next we have to generate the token embeddings from the token IDs. So that's why we needed to maintain the order, because otherwise the LLM wouldn't understand the context. So that's why order preservation is so important. So next we'll get started with the next job, which is the token embedding job. Here, if you can see on the left hand side, there's this token embedding job. So we'll now create the token embedding job. Um, and for that, here we'll need to add the steps for that job as well. So now we will talk about the next job, which is the token embedding job, which will process the token IDs we generated from the previous job, and the token IDs were in the order of the input, like which meant we were able to maintain the order of the input. And this job, the tokenizer job, will generate the vector embeddings for each token, and like it will take the average in the reducer. So that's why we are able to achieve distributed computing. Uh, in this project. Like we are passing the token IDs in the mapper, which then is passed to the reducer. And in the reducer, like in the mapper, it generates the vector embeddings, and then in the reducer, it averages the vector embeddings for each token. Let's add the step for this job. We'll name it token embedding job. And we'll select the path of the jar, right? And I'll copy this command, MapReduce token embeddings. So here we are providing the output path, and this is the input path. And if you closely observe, this is the input path of the, like this was the output of the previous token. Sorry, I forgot the name. Tokenizer job, which then created the token shard. So that this is that path. If you see here, this is the path that we have provided as the output, like as the input for this token embedding job. So it will pick up all the shards from there. So now let's start it. So this is the job, which is a very important job, because here the main training will happen of the like machine learning model. So we have used deep learning 4J library for this. Uh, Here we have used deep learning 4J, and we are training the model using we have created a neural network model, and we are using the LTSM layer as with it as well, so that the LTSM layer is like it understands the context of the words better. And then we are training the model, and the data set, how we are generating the data. So we have created an input array of the tokens, like of the shards in the tokenizer map. Well, not sorry, not the tokenizer mapper. Um, it's the token embedding mapper. So we have created the arrays, like we have created the sequence of the like tokens we have got from the input, like the shards of tokens. And then we have created like the vocab size is the unique tokens in a like in the input. the number of unique tokens in the input split of a mapper. So that is the vocab size. And in each mapper, like machine learning model will get created, and the vector embedding for a particular token will be generated. We are mapping the tokens with index as well, because here, as you can see in the previous, here, if you see, like a lot of the tokens are very large, like it's 2450. So this is very large. So what we are doing is like we can get array index out of bound exceptions, because the machine learning embedding matrix that we'll create is from 0 to vocab size -1, where vocab size is the number of unique words. So that's why what we did was we mapped these tokens to indexes, so that we can like create a smaller array from the embedding size. We don't have to create so large arrays, because if the token generated is 1 million for a particular token, for a particular word, we don't have to create an array of size 1 million. So that's why we have mapped the tokens to indexes. And then we have created the sliding window pairs. Like we have used the like algorithm of sliding window to generate input and target pairs. And like then we have trained the model, like we have called them build the model and then train the model. And then we have extracted the embeddings. And then in the reducer, we will take an average of this embeddings. We will take the average of these embeddings for each token. And let me show the model util class as well. Here we have trained the model and extracted the embeddings. So I just wanted to give a brief overview of the code as well, so that it's easier to understand. And let me like know if you guys have any questions, post in the comment section. All right, and now we'll wait till the job is finished. So the job for vector embeddings has finished. And as you guys can see, this is the token embedding job. And this is finished. So this is the logs. As you can see that it has been completed, like mapper 100% reducer 100%, it has completed successfully. And we want to see the output of it. So this is the output embeddings folder that we provided, and this is the pada0 files. So here are the embeddings of the words. So here it is like not that much understandable. So I'll try um, like opening it in the terminal, because it is more understandable there. So let me just run this command so that we can see the pada0 files. So this is the pada0 file for the first reducer, like which was generated. So as you can see that this is suppose the word wish, and then visions, visitor, visit. So these are the words. This is the word. This is the associated token ID with it. And this is the vector embedding, like the average which was generated for that particular word. So here are the words wait, vote, and so yeah, these are the words. And if you notice one thing, like if you might think that why is this word when or venient or vener, vent, like these type of words, like the subwords, like are present, like unction, unct. Why are these present? Because these are present because when JTOKit tokenizes the words, it tokenizes like there's not one token associated with a word. Like sometimes for big words, there will be multiple, like there will be an array. Like for a word, for example, adjustment, there will be 2 or 3 tokens, like because it JTOKit, like byte pair encoding tokenizes the subwords as well. There will be a token for add or meant, like the subwords for in adjustment. Because these words are present in multiple words. So that's why there are these subwords then Eulivian, and these type of subwords are present. So this was the output of the embedding file. And now what we will do is we will move on to the next job, which is we need to calculate the cosine similarity between the different embeddings. And for that, we need to do one step first. We want to merge the the token embeddings into one embeddings.txt file. And I'll tell you why I'm doing that. So let's run this command to merge the part_r00 files for multiple reducers into one file. So I'll be running it in this command line. So do cat output embeddings parts. Let me just verify quickly once again that this is the path. Yeah, output embeddings part R00. So there are, if you can see, there are three part R00 files. So what we will do is we will merge the part R00 files here, all right, into an embeddings.txt, and I'm creating an input cosine folder for that. So now this has been created. Let me just quickly verify that it has been created. Cosine embeddings.txt. Yeah, this is the embeddings.txt file. It is present there. And so now let me tell that why we are creating this embedding.txt file, because we now need to calculate the cosine similarities between all the words, like all the tokens that have been generated. So if you think there are n tokens, so then we need to do n square comparisons, like pairwise comparison. We need to calculate the cosine similarities. So for that, what I am doing is I am passing this token embeddings into the cosine similarity mapper, and then which then passes the cosine similarities like as the word as the key and the embeddings as the value to the reducer, which has a setup function, because we want to calculate the token embeddings, like the cosine similarity of the token embeddings for one pair, like for one token with all the other tokens, with the rest of the tokens. So a reducer needs to have a particular reducer needs to have access to all the token embeddings of the other tokens as well. So we have created a setup method where it is loading the all embedding txt file, because we have added the all embedding txt file in a cache file while setting up the job. So the reducer loads this all embedding .txt file cache file in the uh, setup method, and then it goes on to calculate the cosine similarity here. It calculates the cosine similarities between uh, the tokens, and then it provides output for the top n, like the top five. Here we are taken a top n as top five, so it will output the top five similar words. So let's see here, we have merged the token IDs. That is why we needed to merge the token IDs, because this token IDs.txt file will be uh, like read by the the reducer in its cache, because it needs the access to all the token IDs. So it will store the token IDs in a map. So let's add the name of this job, another step, cosine similarity job. Let jar again. I know these are repetitive steps and you guys are probably getting bored, but sorry, I'll try to finish it up as quickly as possible. So here I need to provide the output, like provide the uh, uh, arguments. So, so this is the cosine similarity driver we have mentioned, and then the output embeddings. So if you remember that this uh, is the output path of the embeddings, like this is where the part R00 files should be, output embeddings. So yeah, this is the path of that. And then This is the output path where the output will be. And then one other thing is we need to provide the embeddings.txt files, like path. Like we need to provide that path. So I'll be copying it from a previous run. So here I'll now run this. So this is the input path, which contains the embeddings. This is the output path, and this is the embeddings.txt file, which contains embeddings of all the part.0.0 files, like all the embeddings of all the token IDs and words. And this job should generate the word as word, then the embedding of that word, and then it will print the next, like the top 5 similar words. So the cosine job has finished running and it has completed successfully. So here, if you see, the cosine job has finished successfully, and we can check the path, like the output path. Then this is cosine, and this has created the part.0.0 files. Here it has created the files like this. Like for a word, there's the embeddings, and then there are the similar words for it. I'll show this in the command line, like then it will be more understandable. So I'm cat and like running the command on output cosine and part.0.0 files. So this is what has been provided as the output. And here, if you see, these are the words. So these are the words. Like for each word, word is the key, and then we are generating the embedding. Till here, it's the embedding, and then these are the words like which are uh, close, like similar to it, like which uh, are occur, like which has the probability or the chances of occurring together. So like with warehouses, structure, disk, and there are other words like venue, and then these are the different words with for whom the embeddings are present, and then like for unexpected, it's the word. Then this is the vector embeddings, and then for that, like there are top 5 words which are like it's more similar. Like the vector embeddings are more similar. Here, these are the similarity scores for each word: 0.49, 0.45, 0.45, 0.44. The similarity scores are like low or like not as high because the data set for this demonstration purpose I've used is a bit smaller, because otherwise it takes a long time to run the machine learning models. So that's why for this demonstration purpose, I've used a smaller data set. But what you can see, like what we achieved here, like we achieved like distributed parallel computing, like distributed computing for the large language model encoder, because we are used multiple mappers and multiple reducers at the same time to achieve our output. So I'll just give a brief overview of what we did from the beginning. So, and at first, what we did was there are 4 jobs that we ran. The word to token job, this is the standalone, like this is a separate job which is not linked to the other 3 jobs. So this one is just for creating the frequency. We wanted to get an understanding of how many words are present like in a data set, and what are the tokens of this word. So for that, we have created this job. And the tokenizer job, it tokenizes the text and generates the order in the order of the input, which the word to token doesn't. That's why this job was created, the tokenizer job, because it creates the output in an order, like it generates the tokens in the same order the input was present. And then there is this token ID, token embedding job, which like generates a token embedding from the tokens that was created in the tokenizer job. And then the cosine similarity job, which creates the cosine, which like calculates the cosine similarity between the different vector embeddings, and then calculates it, and then generates the top 5 similar words. So that's it. So this was the first part of our project, creating the LLM encoder, and like we will then go ahead and create the other parts, the next part of the homework where we'll create the entire LLM, the decoder. So we'll meet again in that video, and do post any questions that you have. And yeah, thank you so much.